Thank you very much for the opportunity to talk to you about some of our work in micro-solvent extraction, where we've been trying to apply to process intensification, which I think is quite important for the audience here today. I'd just like to acknowledge that I'm working not alone, with Xingfang Zhao and Luke Parkinson, Rossen Sedev, and John Ralston, and we're at the Ian Walk Research Institute at UniSA. The problem that I want to discuss today is actually, it was actually something that was done, worked on during an Amiro project, and so Wayne has actually alluded to it already, but I want to go into a little bit more detail and show you what we've specifically been doing. Solvent extraction is an excellent method for the separation and purification of chemicals when the conditions are just right. And if you've ever worked with solvent extraction and you've worked with conditions that are not quite right, you would know that the process can then become very costly, can be very inefficient, and can even close down a plant temporarily. What you see here is an example of a perfect, if you like, solvent extraction of copper using an oxime. And what you see is that this nice oil phase here with the extractant becomes black as the copper is transferred. And the intermediate stage here is, of course, to disperse the phases so that you can get a nice quick transfer. But as you might know, in mineral processing, chemical synthesis, in particle synthesis, and many other applications in industry, you are often dealing with imperfect solutions, and so you can have major problems. The high extraction rates that you require in liquid-liquid solvent extraction requires high interfacial area, and so what you do is you shake these two phases together or mix them in a mixer, and something like this will occur, but I'll show you these movies in a second. On the left-hand side, this is a perfect system, if you like, pure, no particles present. On the right-hand side, you've actually got nanoparticles present. And you'll see in these two movies, oh, yeah, I'm going to have to listen to it too. You'll see in these two movies that a very different result occurs. You see the phase separation is incredibly fast here. In about 30 seconds, you've recovered your two phases. And in the right-hand side here, next to nothing has happened in the same time frame. Of course, this is what you want in industry, and this is what you sometimes get, maybe not to this extent, but we want to deal with these sorts of solutions here, and I'll quickly stop that. So what's happening on the right-hand side is particles going to the liquid interface and stabilizing these droplets in the system. And if you look closely here, you'll see dollar signs everywhere. So what is the question? Can we bypass this liquid mixing and separation stages to speed up and clean up the solvent extraction process? And we think we can. And as alluded to before, microfluidics seems to be one way that we can approach it. What we've got here is a schematic of a well, here's the microchip. This is what it looks like. It's just a glass plate in this case with some channels inside it which look like this. You have two phases that flow together and then are divided at some point. And of course, the extraction takes place where they're in contact. The dimensions are small on the sort of tens of microns, hundreds of micron scale, and so you've got the same sort of surface to volume ratio that you've got in your conventional solvent extraction, but no droplets. And so you get rapid extraction without droplets. You get mixing and separation instantaneously. You can control the extraction time to within a fraction of a second. And of course, you've got a closed system, so you don't have to worry about fire risks, for example, from volatile organics being above your mixer and settler. It's also operated by flow alone. There's no moving parts in this. It's a simple process where you pump liquid through. I want to show you a case study. It is based on minerals processing, but the audience is wider here today, and I want to just flag that, of course, these sorts of principles that I want to show you can be applied across the board, but mineral processing is one particular challenging example, which is why we chose it for a demonstration. And so again, using the same system that I've showed you already, we've now added about 6% of silica particles, nanoparticles to the system, and you get this particle stabilized emulsion in conventional extraction, and up to 40% loss of your liquid, your organic phase, to this emulsion, and of course with your copper, in this case, your product that you'd like. The emulsion that you form is stable for 6 months, so you really have no chance of recovering this, even if you wait for a very long time, and it's very difficult to process these retrospectively. Now I want to turn your attention to the microfluidic extraction to show you that we're not using model systems here, but in fact real ores. We've taken a copper oxide ore, we've crushed it up, we've done the leaching process, and you can see the nice copper sulfate solution above a sedimented residue from the leaching process. And then we put it through our microchip, as you can see here. So what happens? Well, in the microfluidic chip, when you look on the microscopic scale, you actually have very well-controlled flow. And what you see here is the phase separation point after the extraction occurs. You can see the aqueous and organic phases are choosing their respective channels. What happens to the particles in these systems? Well, the particles in the aqueous phase can be seen using light scattering, and you can see that they've branched into the aqueous channel nice and cleanly, and the organic phase is going in its own direction without the particles, which is a very important point. What you see is the process is not interrupted by the particles. You don't get loss of liquid or the product. And interestingly enough, because we've matched the surface to volume ratios with the conventional bulk extraction, we get the same extraction kinetics occurring. This black line is what you get in a bulk case, and the black and blue and red data points are different particle suspensions that have gone through this device, and you can see the copper extraction is comparable. So if you think about the phase separation times that can be involved in industrial processes, and you take into account that the only time required in this chip is actually the extraction time, you now have a faster overall extraction. And I will just flag there that, of course, the throughput of this is much less than you would expect in industry at the moment, but this is an ongoing challenge that we're about to embark on. So what am I really talking about? Well, just for visualization, this is the first computer that was ever made, and it would do some pretty simple calculations. And this is your iPhone. And I'm not suggesting that we're going to turn Olympic Dam into an iPhone, but what I am saying is that this is the sort of transformation that is available to industry that takes up microfluidics in their processes. And we're really excited about what opportunities there could be. So we should think quite broadly about this. And what does it look like already in industry? Well, this is just a few examples, some pictures of devices that are considered microreactors in industry already, processing tons of material a year. And these sorts of devices, of course, are using the same sorts of principles that I've talked about in our talk. And so we want to bring that to solvent extraction also. Just to say that we, of course, have protected some of this work and through iTech. But what stage of development are we? We're at the small scale proof of concept being complete, and we've shown it for mineral leach solutions, which are arguably some of the more difficult examples. We've already extended to precious metals and using novel reagents in these systems. But integration of these of the separate processes into single chips is an exciting area for the future. We'd also like to explore the opportunities for other industries, and we'd like to target higher throughputs. So what is the opportunity today? Well, this is really an opportunity for a step change in the way that we do these sorts of industrial processes with liquids using microfluidics in the future. And there's really an opportunity to put the lab in the process circuit with microfluidics, and I can talk to you about that later if you'd like to discuss it with me. So we're looking for partners. We are obviously engaged with the MIRA, but we're really looking for opportunities to exploit the new technology, to apply it in current processes, to advance the technology for future applications, and also to explore the opportunities for industrial microfluidics, to really bring this small scale, the advantages of the small scale to the large scale. My details are there. I'd love to talk to anybody, and I look forward to your questions later. Thank you.